Light does what? Light can't decide what it wants to be. Electrons can pass through two doors simultaneously. Welcome to wave-particle duality, the quantum mystery that shows reality itself has an identity crisis. For centuries, scientists argued about light's true nature. Isaac Newton in the 1600s insisted light was made of tiny particles, corpuscles bouncing around like microscopic billiard balls. But in the 1800s, scientists like Thomas Young proved Newton wrong. Young's famous double-slit experiment showed light creating interference patterns, waves of light canceling each other out and amplifying each other. Only waves could do this, not particles. Case closed, right? Light was definitely a wave. Then came 1905, and Albert Einstein shattered everything with one simple observation about something called the photoelectric effect. Einstein studied what happens when light hits metal and knocks out electrons. Here's the puzzle. Dim blue light could knock out electrons instantly, but bright red light couldn't do it at all, no matter how intense. If light were just a wave, brighter light should pack more punch. But Einstein realized light comes in discrete packets of energy called photons. Blue light photons carry more energy than red ones, enough to kick out electrons. Red photons, no matter how many, are individually too weak. This discovery won Einstein the Nobel Prize and proved light behaves like particles. But wait, what about those wave interference patterns? How can light be both waves and particles? The double-slit experiment reveals the truly bizarre answer. Fire light at two parallel slits, and you get an interference pattern on the screen behind, proof that light is a wave, passing through both slits simultaneously. But here's where it gets weird. Fire light one photon at a time, and individual dots appear on the screen like particles hitting it. Yet over time, these individual particle impacts somehow create the same wave interference pattern. Each single photon must somehow be interfering with itself, going through both slits as a wave, then arriving as a particle. It's as if each photon exists in multiple places at once until it hits the screen and decides where to appear. In 1924, physicist Louis D. Broglie dropped another bombshell. If light can be both wave and particle, maybe matter can too. He proposed that electrons, protons, everything, has both particle and wave properties. Scientists thought this was crazy until 1927, when Clinton Davisson and Lester-Germer fired electrons at a crystal. The electrons created interference patterns just like light waves. Particles of matter were behaving as waves. Today, we routinely use electron waves in electron microscopes to see individual atoms. The wave nature of electrons gives us images thousands of times sharper than light microscopes. We've built entire technologies around matter acting like waves. Wave-particle duality reveals something profound. Reality at the quantum level doesn't fit our everyday categories. Quantum objects aren't waves or particles. There's something entirely different that can manifest as either, depending on how we observe them. When we look for wave behavior, we find waves. When we look for particles, we find particles. The act of measurement itself determines which nature we see. It's as if reality is fundamentally undecided until we force it to choose. This isn't just philosophical. It's the foundation of quantum mechanics. Quantum computers exploit this duality, using particles as waves to explore multiple solutions simultaneously, then collapsing them into particle-like definite answers. Today, wave-particle duality powers our technology. Lasers work because light behaves as both electromagnetic waves and discrete photons. Solar panels convert individual photons to electricity, while relying on light's wave properties for efficiency. Medical imaging, computer chips, LED lights, all depend on our understanding that matter and energy have this dual nature. Even more amazingly, Scientists have demonstrated wave-particle duality with increasingly large objects. In 2019, researchers showed that massive molecules containing over 2,000 atoms still exhibit wave-like interference patterns. Wave-particle duality teaches us that nature doesn't care about our human categories. At the quantum level, reality is far more fluid and mysterious than our everyday experience suggests. Light, matter, and energy aren't things with fixed identities. They ray possibilities that become real only when we observe them. The universe isn't just stranger than we imagine. It's stranger than we can imagine.